Lesson. I'm Miss Lee. Today we will continue to investigate the question, what causes an object to stay at rest even when a force is exerted on it? Are you ready? Grab your pencil and your science journal and let's get started.
Look at this object. Have you ever seen anything like it before? This object is actually a work of art, a hanging mobile. This artwork is called Triple Gong, and it was created by artist Alexander Calder in 1951. What do you notice about the mobile? I noticed that there are fewer pieces on one side of the mobile than on the other. I also noticed that the pieces on the right side are larger. Triple Gong is special because it's a piece of art that hangs from the ceiling. Do you notice that a cable is attached to the mobile? We know gravity pulls down on the mobile, but we also know that the mobile doesn't fall to the ground. That tells me that the forces acting on it are balanced. Let's try to model the forces acting on the mobile. Here's our virtual student Michael using his hands to model the forces. Connect your hands like his with one hand above and the other below and clasp them together. The bottom hand represents gravity pulling down on the mobile. The top hand represents the force acting in the opposite direction. If you pull down with your bottom hand to represent gravity, how do you keep your top hand from moving down? To keep his hands from moving, Michael has to pull up with the same strength that he's pulling down. Did you notice the same thing? By pulling up and pulling down with the same strength, Michael is able to keep those forces balanced just like we see in the artwork. Do you notice that this artwork is made of many different pieces that are connected together? We know that the force of gravity is pulling down on each of these pieces, and the force pulling back in the opposite direction is balanced, just like we modeled with our hands. Imagine that you're Calder creating this mobile. How do you think Calder's understanding of forces might have influenced how he designed his artwork? Well, Calder had to think about the pushes and pulls or forces that are acting on every individual piece that makes up this artwork. He had to make sure the forces of gravity acting on each piece was balanced by a force acting in the other direction. That's why the mobile is able to hang together the way that you see it here. Gravity is only one force that we learned about in our lessons. What other forces have we explored? Oh, I know, friction. Let's add what we learned about friction to our anchor chart. What should we write? When we conducted our investigation of how far a ball rolls across different surfaces, we found that the ball rolled a shorter distance across a rough surface, such as artificial grass, and further across a smooth surface, such as rubber padding. Why did the ball roll different distances across different surfaces? Because of friction. We learned that friction is a force exerted between the surfaces of objects in contact. It can cause a moving object to slow down and stop. We also investigated friction with an Atwood machine. We placed pennies into this cup one by one. Even when we added up to 5 pennies, the block stayed at rest. The force of friction was stronger than the force exerted by the cup and pennies. How can we add this additional information about friction to our chart? It can also cause an object at rest to stay at rest when another force is exerted on it. Your first task will be to update the anchor chart in your science journal. Now let's use what we've learned to help us update our anchor model. How can we apply our new understanding of forces to explain the motion of a soccer ball in space compared with the motion of a soccer ball on Earth? Well, what forces should we add to our anchor model to explain a soccer ball's motion? Let's start with the soccer ball's motion here on Earth and focus on what happens when a person kicks the ball. We know that the person's foot exerts a forward force on the ball, but is that the only force acting on the ball? No. Now we know that friction is acting on the ball to slow it down. Now we can also update our explanation. We learned that the ball won't move unless the force exerted on it is stronger than friction. So let's add to this sentence. During a kick, a person's foot exerts a force on the ball that is stronger than the opposing force of friction, which causes it to start moving. Now let's add some detail about how friction affects the ball's motion. After a kick, It slows down as it rolls because friction acts in the opposite direction of its motion. Next, let's update the International Space Station side of our anchor model. Do you remember this video clip of the crew playing soccer on board the International Space Station? Let's watch it again to get us started. So, do we need to add friction arrows to the side of the model? Does the ball slow down or come to a stop? Well, we see in this video clip that the ball changes direction when it hits something or somebody. But if the ball is not in contact with the ground or with any other surface, can friction affect its motion? No, it can't. So we won't add friction to our drawing, but we can update our anchor model explanation. That's right. It also doesn't slow down and stop because it isn't in contact with the ground, so friction doesn't act in the opposite direction of its motion. Your second task for today will be to update the anchor model and explanation in your science journal. Our anchor model is an example of a force model because it uses arrows to represent the forces acting on the soccer ball. Remember that we also made force models for the Atwood machine. You know, we've learned a lot about how forces can move objects or keep those objects at rest. But in all of our investigations, we've seen objects in contact. I wonder, can objects move without being touched by a person or another object? Hey, wait a second. That question is one of the unanswered questions on our driving question board. Let's use this question to make a new category. How can an object move without being touched? Do you have any other questions about whether objects can move without being touched? Here, let me show you another interesting video clip. Ready? These kids are playing some sort of game. Whoa, did you see that? Some of the game pieces move without anyone touching them. What questions do you have about the changes in motion you observed? I have a lot of questions. First of all, I want to know, how can objects move without something touching them? I also wonder, where is the force that makes the game pieces move coming from? And why can't we see what is causing the force? We know that gravity pulls objects down, so I don't think gravity pulls the game pieces across the board. I wonder, how is this force different from gravity? Let's add these to our driving question board. It seems we've got some more investigating to do as we explore the question. How can an object move without being touched?
Hi, students, and welcome to today's lesson. I'm Miss Lee. Today, we will complete the Concept 2 conceptual checkpoint. Are you ready? Grab your pencil and your conceptual checkpoint, and let's get started. Ice hockey is a sport in which players hit a puck with a stick to try to score goals. Watch this short video clip of a child playing hockey. As you watch, observe the motion of the puck. Imagine you are playing ice hockey. A puck is at rest on the ice. You hit the puck with a hockey stick. The puck slides across the ice. Question 1. The top row below shows 3 force models of the puck at different points in time. Each diagram in the bottom row represents the motion of the puck in one of the force models. Under each diagram, write the letter of the matching force model. Then, under each force model, write the title of the matching diagram, before hit, during hit, or after hit. Question 2. Look at the force model you labeled before hit. What forces act on the puck before the hit? Are those forces balanced or unbalanced? How does those forces affect the motion of the puck? Question 3. Look at the force model you labeled during hit. What forces act on the puck during the hit? Are those forces balanced or unbalanced? How does those forces affect the motion of the puck? Question 4. Look at the force model you labeled after hit. What forces act on the puck after the hit? Are those forces balanced or unbalanced? How do those forces affect the motion of the puck? Your task for today is to complete the Lesson 18B conceptual checkpoint.